Mm, 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 mm. I think I am visible now. Mhm. Good afternoon, guys. So, this stream is going to be about compression algorithm. We are going to learn compression algorithm in this particular stream, try to figure it out how it works, and get as much as knowledge we can from the compression algorithm. And I have done the last stream. Who is from the last stream? I've done it on what is the topic? Okay, so we were creating the Chrome extension by using vibe coding, right? So for that, we will continue it in the evening, most probably, if we like, if we want to create. Otherwise, till then, let's start with the compression algorithm. Data compression is a fundamental concept in computer science essential for reducing the size of data to save storage space, speed up transmission, and optimize performance across various applications. Where it's compressing a file before sending it over the internet, encoding video streams for efficient playback, or reducing the size of massive dataset. Data compression plays a crucial role in modern computing. Compression algorithms are classified into two broad categories: lossless and lossy. Lossless compression ensures that the original data can be perfectly reconstructed from the compression data, making it ideal for the text, files, software, and other data uh, where precision is critical. On the other hand, lossy compression allows the some loss of data fidelity, often imperceptible, and wait, I have okay. Data compression, right? Mm-hmm. Okay, so data compression, right? Fundamental concept of computer science essentials. Okay, so let's start with the data compression, I guess. That will be better. Hello, hello. Okay, so data compression is a fundamental concept in computer science essential for reducing the size. Okay, I've read this already. Lossless compression ensures that the original data can be perfectly reconstructed. Okay, um, making it ready for text software and other data where precision is critical. On the other hand, lossy compression allows some loss of the data. Yes, it's done. This article dives into the mathematical foundation and mechanism of various data compression algorithms, both lossless and lossy, and explore the real-world applications. Fundamentals of data compression, entropy and information theory. Entropy, I know that entropy, it measures the unpredictability and randomness of the data sources. Introduced by Shannon in the context of the information theory, it qualifies the average amount of the information produced by stochastic stochastic source of data. The entropy hx of a discrete random variable x with possible values x1, x2, and to the xn are corresponding the probability mass function px given by hx equal to summation n upon. Okay, so this equation shows the randomness, like possibility of the randomness, that no, the entropy of a discrete hx, okay, of a discrete random variable x. So HX shows the randomness, what I can guess it from there. Okay, so entropy represents the minimum average number of bits required to encode the source symbol. A higher entropy indicates the data is more random and less compressible, while lower entropy suggests the data contains redundancy, which can be exploited by the compression algorithm. Entropy represents the minimum average number of bits required to encode the source symbol. Okay. Higher entropy indicate that data is more random and less compressible, while lower entropy suggests that data contains redundancy, which can be exploited by compression algorithm. This means if we have a PDF and we just want to find that data is compressible or not, because since compression is work uh, on reducing the bits, like most of the time, that's how it works. So if the entropy is high, that means randomness is high, so we cannot compress that, because when randomness is high we have to use more notations and, like, let's say, more number of decoding and decoding, which will eventually lead up us to more data storage instead of lower data storage. That's what I can think of. Redundancy refers to the presence of excess data that is not essential for the conveying the intended information. In data compression, reducing redundancy is a key to achieving more compact representation. Written data can often be printed or represented in a shorter form without losing information, or for instance in a text file, the repeated occurrence of a word like the can be encoded more efficiently by assigning a shorter code to it. Okay. Okay, so redundancy means, like, we have entropy, then we have redundancy. Redundancy means if we have excess data which is not required, so it will be what's cooking. Okay, so it will be achieving more compact. Okay, means if we just remove those data which are not essential for our data set, this can also be called a data compression by reducing the redundancy, right? That's what we can get it from here. Reducted data can often be predicted for or represented in a shorter forms without losing information. For instance, in a text file, the repeated occurrence of the word like the can be encoded more efficiently by assigning a shorter code to it. Okay, so we have the, okay, so we can just assign shorter code to it. That will be, I guess, the way. That's what this article was trying to say. So let's move to our next part, where source code coding theorem. Okay. Shannon's source coding theorem state that entropy hx of a source lossless compression. According to this theorem, no lossless compression algorithm can reduce the average number of bits per symbol below the entropy of the source. This sets a fundamental limit on the efficiency of compression algorithm. Shannon source coding theorem states that the entropy Hx of a source represents the theoretical limit of lossless compression. Okay, according to this theorem, no lossless compression algorithm can reduce the average number of bits per symbol below the entropy. According to this theorem, no lossless compression algorithm can reduce the average number of bits per symbol below the entropy of the source. This sets a fundamental limit on the efficiency of compression algorithm. Okay. Hmm. This means that the entropy which we get from the formula is going to be the theoretical limit of lossless compression, because below this compression, no lossless compression algorithm can reduce the average number of bits. Okay, so let's say if we have the entropy is high, we cannot perform the lossless compression on that, because we don't have that much we don't have that much storage to like storage node, like algorithm to store the random data and compress it, because in the compression we mostly just try to reduce the number of bits, which means, for let's say we have a repeating word called a in a sentence, and it have 10 times and the length is only 12, so we can store it in 3 bits, just like saying that okay, a is 12 times, no, I mean 4 bits. Yeah, so that's how it work. But if the randomness is more, this means that we don't have that continuous data of like 2, 3 or 4, then it will be more tough for us to do the to do this. This is what I can get from this. Okay, so we have lossless compression algorithm. Now we have the first compression algorithm is Huffman coding. I know about Huffman coding, like not Huffman coding. I've I've uh, read this about in my second year, first sem, like third semester, I guess. Yeah, in my third semester, I studied about the Huffman coding. It was something like binary graph where we have to store the data on the basis of what is bigger and what is smaller, and then we will just map the data to get it from the graph. That's what I think. Okay, so Huffman coding is widely used lossless compression algorithm that assigns variable length code to input character based on their frequency. Character that occur more frequently and assign shorter codes with less frequent character receive a longer code, resulting in more efficient overall encoding. Okay, so I know about this, that let's say we are forming a tree. Okay, so what we are going to do? Etc. That way. Okay, so let's say we have here we have few numbers. Let's take an example. Mississippi. Okay, this will great. So we have Mississippi. Okay, so let's say if we create the table for this. Okay, so I have one viewer who is it. Okay, so we have Mississippi means let's say we have to find the occurrence, right? So what it is saying that the number of occurrence is related to the placement of the element in the leaf, I mean in the tree. So let's say we have the number of occurrences high in of a word, this which means that it will be on the root. And if we have the low occurrence of the letter in a word, then it will be on the bottom, means on the leaf. That's what I can say. And which means if we form the table using this, so MISP, Mississippi, MISP, ISP. Okay, so we have three words, MISP. Now let's see that what is happening here. So we want occurrence. So occurrence means how many times it came in a sentence. Which means if we see that about M, it's only one time. Then we have I, it's four time. Then we have uh, S, it's four time. Yeah. And then we have P, it's two time. Okay. So MISP. Okay, so now if we see that, so the numbering will be done like where what will be the leaf and what will be the root will be dependent upon the occurrence. The number of occurrence is higher, the leaf and root will be dependent upon that. If the no occurrence is higher, means that we have to assign it the lower bits, the lower bits, because see, if something is occurring again and again, means in the sentence we need to use the same number of bits again and again. This means it can cause to a very extra storage, or it can cause the lots of storage in storing the file, right? So let's take this as an example. Now, how does Mississippi works? So if we create, let's say in the bottom we have M, right? Then we have P, and if we sum both of them, then we have 3 because it's 2 and this. Then if we take 4, 4 means we have 8. So if we just take, okay, so We again have 4, so we'll place it here. 4 means, let's say, this means that in the top it will be 11, right? So if we just assign the numbers, so we have 0, then we have 1, we again have 0, we again have 1, we again have 0, we again have 1, right? That's how it is going to be look like. That's what I can think of right now. And if we have to access p, then how we are going to access 111. If I going to access m, then how we are going to access 100. My bad, 110, sorry. Then we have to access uh m, p, and then 4. Wait, 4 is I and S. So instead of that, if I write I and if I write S, okay. So if I have to access, I can just go to 0. Otherwise, I can do 10. Okay. So I think that's wrong. That's not what we can do. Let me just create a leaf node for each character and arrange them in priority queue based on the frequency. Repeatedly extract the two nodes with the smallest frequency. Create a new node with the frequency equal to the sum of two nodes and add this new node back to the queue. Continue until only one node remains representing the root of the Huffman tree. Back to the queue. Traverse the Huffman tree to assign binary codes to each character with left branches represent 0 and right branches represent 1. The optimality of the Huffman coding comes from the fact that it minimizes the weighted average code length, which is closely related to the entropy of the data. Example, consider a message considering of the characters A, B, C, D with frequencies 0.4, 0.3, 0.2, and 0.1. The Huffman tree construction would yield a binary code such as 0, 10, 110, 111, resulting in more compact representation that using fixed length codes. Arithmetic coding. Arithmetic coding is another lossless compression technique that differs from the Huffman coding by representing the entire message as a single number, a fraction between 0 and 1 instead of assigning codes of individual symbol. Arithmetic coding encodes the message's continued interval on the real number line. The process involves internal division. The probability range 0, 1 is divided into subinterval based on the probabilities out of the symbols. Encoding the message is encoded by successively narrowing the interval to reflect the symbol in the message. Final output. The final interval is represented by a single binary fraction. Okay. Internal interval division, encoding, and then final output. Mathematically, if a message contains symbol with corresponding probabilities, the new interval of Si is a plus b minus a dot. Okay, so I can't understand that. If a message contains symbols, okay, with corresponding possibilities p1, p2, and pk, the range of each symbol Si in the current interval ab is determined as follow. The new interval for Si bracket square bracket a plus b minus a, okay, where FSI is the cumulative probability of SI. Okay. Example, for binary message with probabilities 0.8, 0.2, arithmetic coding would represent the message 011 as the fraction like 0.425 and coded as binary. Okay, fraction like 0. Means here what we do, that we use from 0 to 1 probability, or you can say fraction fraction to store the data and do the coding and encoding part. Now run length encoding, RLE. So what is RLE? Means run length encoding is a simple yet effective compression technique, particularly well suited for data containing long sequence of repeated character. Instead of storing each character individually, uh, okay, RLE compresses data by recording the character and the number of time it repeats consecutively. Mathematically, in a sequence contains a character x repeated n times. RLE represent this as x comma n. Example, for a sequence A, okay, RLE comprises 5a, 4b, 4c. Okay, so that's the very simple part. Like run length encoding is something that is very simple. Now let's move on to lempel dash shift dot welch. LZW is a dictionary based compression algorithm that builds dictionary for the substring encountered in the input data and encodes them these substring using reference to the dictionary. The LZW algorithm works as flow. Initialization. Initialization starts with dictionary containing all possible single character strings. Processing inputs read a sequence of character, and if the sequence exists in the dictionary, continues reading until a sequence that is not in uh wait okay the dictionary is counted. Okay, dictionary updates. Add the new sequence to the dictionary and encode the longest matching sequence found with its corresponding dictionary entry. Mathematically, if www represents the number current sequence and kkkk the next character, the new sequence wkwk is added to the dictionary. Example, for string ab, lzw would recognize repeating patterns and encoded the string using reference to previously seen patterns significantly compressing the data. Lossy compression algorithms. Transform coding. Transform coding is a lossy compression technique commonly used in image and videos compression, where is the goal is to reduce the amount of data required to represent the signal by transforming it into the domain where the important information can be more easily compressed. Okay. The discrete cosine transform DCT is one of the widely used transforms in image compression, e.g. JPEG, and DCT transform spatial data into frequency components, allowing for the separation of high frequency components from low frequency components. Okay, so what does it mean? That the discrete cosine transform DCT is one of the most widely used transforms in image compression. Example, JPEG. The DCT transforms spatial data into frequency components, allowing for the separation of high frequency means details components from low frequency smooth components. Mathematically, the 1D DCT of a single action is of length n is given by xk summation of n minus 1, and where n equal to 0 it's starting. Okay, so we have this equation. The DCT coefficient xk, and xk represent the signal in the frequency domain. During compression, many high coefficients are quantized or discarded, resulting in data low that is often imperceptible to human vision. In JPEG compression, an 8x8 block of image pixel is transformed using the 2D DCT quantized and then encoded. The quantization process discards less important information leading to compression. Okay. Vector quantization. Vector quantization is a lossy compression technique for approximates data vector by set the representative code vectors. VQ is particularly useful in image and speech recognition. The VQ process can be described as follows. Code code book generation. Create a code book consisting of finite set of vectors. The best represent the data. Encoding. Replace each input vector with the nearest code word in the code book. Mathematically, for an input vector x, we have math- uh, okay. So thing is here, the thing is in lossy compression, we are focusing on reducing things. Let's say we are just trying to figure it out. What's not important, reduce it. So we are going to lose the data, right? But when it comes to the lossless compression, we are mostly focusing on how the repeating things should be stored. So we cannot, we like our file should not take that much space. That's what I can think of. Okay, so any guy who know about compression algorithm can also just start chatting, ask me the questions. Okay, so run length encoding means when you are working on the arithmetic coding, okay, then it makes sense, right? You are just using the probability, or you can say the probability of that word to give them the index, right? Let's say we have a probability of a word is something like 0.676, then 76 might be this word. That's what it is doing. That what I can think of. Now when we comes to the run length encoding, we are just doing the simple run length encoding where we are using the, you know, let's say we have letter like this. So this was the Huffman encoding where we were using Huffman, which is totally wrong. Like this tree is totally wrong. I don't know about the Huffman. I have to learn it. I'm just going through it. So what I can understand from the run length encoding is that let's say we have AAA, BBB, CCCC, DDD. So this, like, we know that one like if we talk about like one letter, let's say A. So we have A here, A equal to 8 bit. That's what we know. A will take 8 bit. So what we wanted, that instead of doing this like A, so total of 8 for the 32 bits, instead of that, we are just going to store it in 2 bits. How will, sorry, I mean in two places. How we are going to do it? We have 4A in a row. So what we will do, that let's say from the AAA, if we just use 4A, then 3B, 3C, 3D, it reduced to the from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 to 1, 2, 3, 4, 5, 6, 7, 8. 8 places. So this makes sense a lot, right? That's why run length encoding is applied in the lossless compression. And the lossless compression has a very big drawback, that it cannot work on a high entropy data that we learned earlier. Wait, where was it? Okay, so we have also. Here you can see we have that entropy and information theory. So when the entropy is high, compression algorithm, lossless compression algorithm will not work properly. In the Huffman coding as well as all the compression algorithm, they are just here in lossless. We are just here to preserve the information along with compressing it. So lossless compression is focusing on reducing the repeating data instead of removing it. It just reduce it. It uses algorithm first to compress that, and then convert it into something like a coded form. And then when you are viewing it, like when you unzip the file, you are going to get that same data but in less amount of storage, right? That's what I can think of. It's like, if you take the example, it's like a folding a paper. If you think about the lossless compression, you are just folding the paper and fitting it into the pocket. But in the lossy compression, you are tearing it down, just taking that, okay, this is the paper, this is how it looks. But if I just tear it down the corners from the, or tear down from half, it will take less storage, but it is a paper, right? And it will work. So that's how things are working in lossy compression and in lossless compression. That's a pretty clear for me. Okay, so let's continue with the lossy compression again. So we were in the vector quantization. Vector quantization is a lossy compression technique that approximates data vectors by a set of representative code vectors. VQ is particularly useful in image and speech compression. The VQ process can be described as follows: codebook generation. Create a codebook consisting of a finite set of vectors, code words, that best represent the data encoding. Replace each input vector with the nearest code word in the code book. Mathematically, for an input vector xxx, the encoded value in the index of the code word y, that minimize the Euclidean distance x minus y. Now, this is something mathematical terms are applied here, so I have to understand it more properly because I don't know that much about this Euclidean. Okay, what is distance? Okay, understood. Means that diagonal distance, straight line distance between 2 points in a space. Line segment. I understood. Understood. Yes. So that's how things are working. Hello everyone who is watching the stream. How are you guys? Anyways, so we have the Euclidean distance x minus y. Okay, so this is what I can guess, that x minus y, if I'm not wrong. It's, wait, it's a something like this. Like if we have graph, so it will be like, we can say that it will look like this, right? And the distance it is talking about is this part, I think. Wait. Okay, so that's understandable that replace the vector input the nearest code mathematically for an input vector xxx, the encoded value in the index of the code word y, that minimize the Euclidean distance x. Okay, example. In image compression, a small block of pixel might be represented by the closest matching code word from the code book, effectively compressing the image by reducing the number of unique pixel patterns. Okay, so this want to say that, what I can get it from there, if you have an image, it will have multiple pixels, right? Something like this. Let's take the example of image. Okay, we have multiple pixel here. This is not what image look like, but okay, we can only make this. Mhm. Mm, this is so satisfying, I guess. Okay, so from this we can understand a lot. So let's say we have these pixels. So when in an image we have colors, right? We have different colors. So let's say this is the blue color. Here we have a blue color, let's say, and we have a light blue here. Uh, wait, light blue. Okay, so we have this. Now these are two pixels, and these are close to each other. Means that whenever we have this particular color, we will say that okay, this is equal to, it should be white. Okay, this is equal to let's say its code word is blue, something like this. So whenever all this color came, it also finds its nearest color and it will assign it to that, right? Here the color will be lost because the blue, that's what I can understand. That's very bad example if you're talking about the compression algorithm, but okay, only thing I can understand properly. If we are saying that we are just rounding off things, let's say we have a number called 1 and 1.1. In the data it's 1.1, but when in the compression we are putting it, we are taking it as 1. So what will happen? It will just lose the data which was accurate. It gives us the data which is so close to that which we entered earlier, right? So that's how compression is working here. That's what I can get from this, that how vector is vector quantization is working. Factor Fractal compression. Fractal compression is a technique that exploits the self-similar nature. Wait, till then, guys, you're watching, but you're not chatting. That's not fair. At least, like, this is something we have to study together. So, if you are familiar to this algorithm, you can suggest me things from where I can learn, like book or a PDF and whatever you want. Okay, so let's go to the Safari again. Okay, so fractal compression. Fractal compression is a technique that exploits the similar nature of the data, particularly in image, exploits the self-similar nature of data, particularly in image, to achieve compression. This method encodes an image by finding mathematical transformations that can reproduce the image using repeated patterns. Fractal compression is a technique that exploits the self-similar nature of data, particularly in images, to achieve compression. This is something which I have to understand. Exploits the self-similar nature of data, particularly in image. Okay, okay, I think I get it, but I can't explain this. Let me just be clear. The key idea behind fractal compression is that an image can be represented as a collection of small parts. That's totally fine. That's how it works. An image is actually a 2D array that, like, as my teacher said, this is a 2D array, right? So, okay, each of which is similar to the entire image, each of which is similar to the entire image or to the other parts of the image. These similarities are encoded as affine transformations, which include scaling, rotation, translation, and reflection. Mathematically, if a portion of the image can be represented by a transformation T applied to another portion, the transform one minute. Mathematically, if a portion of image can be represented by a transformation T applied to another portion, the transformation parameters are stored instead of pixel values. Okay, so that transformation which is taking place inside the pixels means like we are just transforming using that fractal compression. So the data which will be stored is not the pixel, it will be the transformed parameters we are using, right? Example, in fractal image, the compression and image of one might be compressed by recognizing the same basic shapes is repeated at different scales throughout the image. Okay, now I get it. It okay, so Same basic shape is repeated at different scales throughout the image. I have to understand this properly, otherwise I'll forget it. Wait, here ChatGPT should help me. Okay, chat. Like, I am 15-year-old. Okay, okay, what is fractal compression? Fractal compression is like spotting patterns in pictures and using those patterns to save space instead of remembering every little detail in an image. We remember how the patterns repeat, kinda like a clever shortcut. Imagine a picture. Let's say you have a picture of fern, a leafy plant. If you zoom in on the fern leaf, you will notice that a small part of the leaf looks just like the whole thing, and another small part also looks like the whole leaf. Right? It's like a pattern repeating itself at smaller and smaller level. That's called self-similarity. Nature loves to do this. Clouds. Okay. Ferns, clouds, trees all have it. Okay. So what does fractal compression do? Normally, computers store image by remembering the color of every single pixel. That's like remembering what every grain or sand look like on a beach. But fractal compression is smart. Instead, it says, hey, this little part of the image looks like the bigger part over there. Just rotate or shrunk a bit. It will remember the rule to recreate it. I'll remember the rule to recreate it, not the whole thing. These rules are called transformations. They tell the computer how to copy one part of the image, change it little, like shrink, rotate, or move it, and use it to recreate another part. Real life analogy. Imagine building a Lego castle. Instead of building the same tower 4 times, you build it once and write down instruction like copy that first tower, move it here, flip it, and you've got the next one. Fractal compression does that with image. So in simple word, fractal compression is like finding repeating parts in a picture, writing down rules for how to reuse them, saving those rules instead of the full picture, then using those rules to rebuild the picture later. Okay, so that's clear now. Means in factor compression we are finding the pattern first. If patterns are found, so what we will do, that we will just find a way that how these patterns are similar to each other. How can we just use one particular pattern to make different patterns by just rotating and shrinking it, and all the patterns which can be made should be will be linked to this particular pattern, and whenever we are going to view this image, the algorithm is going to help us to recreate the image by just using these patterns. It will remember the patterns which was on the image. So that's what it is trying to say. It is a kind of pattern recognition system, and it have encoding and decoding. Encoding removes the repeating patterns and keep only one, and decoding does what it does, that it keeps the note that how image was looking. When encoding, it just encode the image with the patterns and create again. So it can have lots of loss, right? Let's say it can create a bad image also, like noisy and pixelated, where we know that pixels are not properly aligned. So yeah, that's why it's lossy algorithm. And in the vector quantization, what we are doing, that we are just finding the nearest possible matches, sorry, match, I mean matches, right? Both are lossy compression. Okay, we have advanced technique in data compression. Okay, let's see what is advanced technique. I am on the basics right now. Okay, so we have 4 guys watching. Are you guys understanding anything? Like, am I explaining right? Okay, anyways, we have velvet based compression such as JPEG 2000 in an advanced method that offers superior. Okay, here's the thing. Here's the thing I am getting right now, that when we talk about the lossless compression, So lossless compression is more about the patterns, as I said earlier, is more about that how can we reduce the number of bits by just finding the repeating patterns, means those data should not be changed or transformed, but just find the repeating patterns, right? But in the lossy compression, what we are saying that okay, a little bit data can be compromised, it doesn't matters. So if we look at the real world examples, what I can get whenever we compress a file, most probably it uses the lossless compression because we don't want to compress anything like in a text file or in a code or in something. When we share it, we don't want to lose any data, and mostly it is the text based data, so it is not random, right? But lossy compression mostly done in terms of when we are using image or voice or audio, something like that, right? So that's how things are working here. So if we talk about the lossy compression, we are mostly talking about the compression which is done in videos, in audios, and more about those content where data is not in the form of string, because whenever we are doing with string, we have patterns which are repeating, we have lots of ways to compress that, and their compression is not like okay from 100 kb to 1 kb, that can't happen, because we have the data which we can't lose, right? Anyone have any comments? Anyways, okay, so borrows. Okay, so in Velvet, wavelet, wavelet transform. Wavelet-based compression such as JPEG 2000 is an advanced method that offers superior performance over traditional DCT-based techniques. The wavelet transform decompose data into a set of coefficients that represent the data at different scales. Mathematically, the wavelet transform involves convolving the signal with a wavelet function which is localized in both time and frequency. The result is a set of coefficient that can be efficiently quantized and encoded. Mathematically, the wavelet transform involving the signal with wave function. Okay. In JPEG 2000, a image is decomposed using the discrete wavelet transform TWT. Okay, and the resulting coefficient are quantized and encoded. The wavelet-based approach also for better compression ratio and image quality, especially at lower bitrate. The wavelet-based approach allows the better compression ratio and image quality, especially at lower bitrates. I have to understand the wavelet-based compression, but this is something which what I can get from this blog is that wavelet is based on waves, more about colors and everything. Let's see what is it. Okay, it's a super smart way to shrink images like without making them look bad even when the file is really small. Think of it like a taking apart an image and figuring out which part are important, which part are details, and then saving only what really matters. What's a wavelet? Okay, weird word, right? Wavelet just means a tiny wave. Imagine a squiggly line that's small and only exists in a tiny part of the image, unlike others, waves that go on forever, like in sound or radio. Wavelets like burst, they are localized, they look at small parts of the image at time. Okay, weird word. Wavelet just means tiny waves. Image a squiggly line that's small and only exists in a tiny part of the image. Okay, so wavelet transform is like using these tiny squiggles to scan your image and say, what do I see here? A sharp edge, a smooth area, some texture. So how does JPEG 2000 use this? Step by step simple version. Take an image, use wavelet to break it down into basic shapes and details at different zoom levels, like looking at big picture and also the tiny corners. Store those details called coefficients instead of the raw pixels. Throw away the unnecessary stuff like tiny details the eye won't even notice. Save the remaining info in a compressed file. Real life analogy. Imagine you are making a Lego model. Again, we have Lego example. First, you make a big blocky shape, then that's over several structure, low details. Then you add similar blocks for rocks, trees, etc. You don't need to save every pebble, just the block that make the mountain look real enough. Wavelet compression does the same. It builds the picture from big important parts and fills in detail only where needed. Why is this better than old school JPEG? Traditional JPEG use something called DCT, discrete cosine transform, which is kind of like breaking the image into square tiles and compressing them, but the method can make image look blocky or fuzzy. Okay, understood. Especially when heavily compressed. Wavelet based JPEG 2000 is smoother. No blocky patterns, better quality at small size, keep more details when they where they matter. In super simple word, wavelet compression like zooming into picture at different levels, keeping the important details and smartly ignoring the parts your eyes don't care about. So the image looks great but takes up way less space. Okay, so that's what it is. JPEG 2000. Let's move on to the Boros Wheeler transform. The Boros-Wheeler transform is a reversible data transformation that rearranges the input data in a way that clusters similar characters together, making the data more amenable to compression algorithm like RLE. The BWT works as follows: transform, generate a matrix of all possible rotation of the input string, sort the rows uh, lexicographically, and take the last column as the output. Reverse transform. The original string can be reconstructed from the BWT output by following a specific process. For a string banana, the BWT would produce, okay, which has cluster or repeated character, making it easier to compress using RLE. Okay. Borrow-Wheeler transform is a reversible data transformation that rearranges the input in a way that clusters similar characters together, making the data more amenable to compression algorithm like RLE. So first it arranges the data and create the clusters of similar character together. That's okay. Transform generate a matrix of all possible rotation and tiny string. Sort the rows, okay, logic lexicographically and continuous transformation. Okay. So what I can understand that like the example, it have banana. The BWT would produce A, okay, and N, P, then dollar AA, which has clusters or repeated characters, making it easier to compress using RL. Prediction by partial matching. Prediction PPM is a statistical modeling technique used in lossless. Okay. Uh, Yo guys, how are you doing? Are you enjoying this or just getting bored? At least please interact, like, so I can just see that who is watching and who is not. Okay, PPM is a statistical modeling technique which uses lossless data compression. It predicts the next symbol in a sequence based on the context provided by the previous symbol mathematically. PPM uses a context model to estimate the probability of the next symbol. The model is updated as more data is processed. And okay, so it's basically a model, AI model, which predicts that what can be the next, right? So these are the new things which came into the market for the compression. That's what I can understand. But the main things are basic, like Huffman encoding, RLE, and that uh, what was that in lossless compression? Okay, lossless compression. We have arithmetic coding. Yeah, arithmetic coding is also something better because here we are using probability, like what is the probability of this particular word in a text. So we are just assigning that because every word will have different probability, means relative probability, not actual. Like if any word have two then it will, the probability will the same, but relative probability to the others, so it should be different. Also at the same time it should hold the probability of that particular letter or word, right? Okay, so what should we do next? Compression matrix, like performance matrix data compression, compression ratio and bitrate. I've learned about this because when I was developing a project which was based on I guess in the industry which was based upon this compression thing. So we just have to check the file compression ratio. So yeah, I know those. Like it's a basic thing. You have original size and compressed size. If you create a ratio, and ratio will be the performance matrix like 5:1. So if we have 10 MB in the size, it compares to 2 MB. The compression ratio is 5:1. Yeah. Now if you see that bitrate is same thing like total bits upon total time. Now the bitrate measures the number of bits used per minute of time in lossy compression, particularly in audio and video. A lower bitrate often results in lower quality, but also smaller file size. Example, for a video stream compressed to 1 Mbps, the bitrate reflects the trade-off between quality and file size. Mean squared error, MSE, and peak signal to noise ratio. Okay, this is something not I have to understand right now. For now, let's move on to that compression algorithm. Compression algorithm from the scratch. So I can create a program now. What I should choose JavaScript as compression, so I can just figure it out. Mm, without libraries. Okay, so we have allowed the customers to upload their document with arbitrary sizes without requiring them to reduce the file size of the. Okay, therefore, this is, I guess, not what I'm looking for. Output.pdf, compressed PDF, define configuration option for XCS request where config. Okay, so I'm not getting it that like I just want to do it from scratch, means by the coding. How does it, like how can I do it? PDF REST API. It is using the API, making the call to the API, then it's getting back. I don't want to use API. So it have everything. I guess. Should I use Golang for compressing PDF files? I think I should because it will be better that if I use Golang for it. I already wanted to learn about the Golang. It will be better for me to understand that how it works. So for that, if I just go to the Golang, s- I think Go is already installed. Yeah, it's installed already. Uh, let's say I have to make compression algorithm. Okay, okay. So we have four people with us who is going to watch that I'm going to code like shit for real because I don't know about Go, like how to set up and everything. I'm just going to experiment it. Now I have to change. Every time I learn a new, if I just use programming language, a neuron dies. Safe. Yep, that's better. Mm, let's say desktop. Okay, my bad. I have made the directory. No, no, I don't want this. Uh, I just want to make the this will be better. Okay, so yeah, that's what we have to do. Dependency tracking for your code. When your code imports package containing other modules, you can manage those dependencies. Okay, I'm ready. Hello, city, hello. Mm-hmm. Init example, hello. For purpose of the story, just example, hello. Okay, so I have to use this go mode init, go mode init. Um, what I'm 'fmt' means fmt dot print. Okay, fmt means like I guess this is the import library. Print ln. No, that's print ln. Hello. What? That's I think what I was trying to say. If I write this and go run dot. So okay, so finally I've ran a code in Go. Just uh just say the congratulations at least, guys. Can I see any congratulations in the chat? I think not. Don't. Uh, okay. So now if we have to, let's say, do anything else, call an external package. Okay. For in Go code, import the code package for and or call its Go function after adding the highlighted lines. You should put the code package and call to its Go function after adding the highlighted lines. Should include the following package when import fmt import rcs I import function main fmt prints code.go import rsc.io.code slash code. Mhm. Mhm. Again, if neurons don't comment by sharing memory, share memory. That's great. Introduce the code. Okay. This is the first part of the tutorial that introduces a few fundamental features of the Go language. If you're just getting started with Go, be sure that you take a look at the tutorial Get Started with Go, which introduces the Go command, Go modules, and okay. Create a model with call your code from another module. Take prerequisite some programming experience. I have home path, Go mod init example.com/greetings, creating new go.mod module example.com. This is the function. Okay, so go mod it into example.com. Example.com. Let's say now if I create go mod file will list the various versions of your code depends on this keeps build reproducible and gives you direct control over which module version to use. In your next editor, create a film in which write your code and call it greetings.co. Okay, greetings.co. Go to greeting.co. Then package, wait, package.go. Yeah, package greeting means we are declaring the package. FMT fun. uh, what I'm writing is message. Okay, so we have this fmt dot printf. Percentage v. I can't understand what it's saying. Okay, greeting for the caller and the ask. You will write the code at the calls. We have. I am a beginner. What I can start? I have already completed Python. What you can start? Are you still there? Can you just say yes so I can just tell you that? Anime. I don't know your name. So are you still here? Okay, so for like you are saying that you are a beginner and what I can start, just start developing, right? On the way you can figure it out on your own that what should you do and what should you not. Instead of asking that what you should start, just start developing and it will help you a lot in upcoming time. Like see, in the beginning of this video I was learning about compression algorithm. Now I'm learning Go. Like I'm going to implement the compression algorithm using Go. So this is something, that's how you learn. That's how you know that okay, so this is the way you can figure it out. Some things on the go, and you have the AI right now. So there's lots of things you can do with AI, understand things. Yep, that's pretty much. Okay, so I okay. Wait for a while, guys. I'll back soon. Okay, I'm back and Mm, in the next step, you can call this function from other module. Let's just take a rest for few minutes, I guess. That will be better. This is what I want. Okay, so how we are going to this? Uh, okay, we'll fix this in upcoming time. Till then, just start. Anyone have any questions or something? Can ask. We have three persons here. At least one of them can respond, right? Okay, so I think I should come back at night for the stream. We'll continue doing that, which was we were doing. So for now, it's time to say bye.